Good morning, good afternoon, good evening, everyone. Today I want to talk about something incredibly tiny, almost invincible, yet powerful enough to force us to rethink one of the basic assumptions of the standard model. We all know neutrinos. They are really small and almost massless. And also, we know that they like to change their identity. They oscillate. And this actually naturally raises a deeper question. What exactly are we detecting when we observe a neutrino? Are we measuring its flavor state, its mass state, or the outcome of quantum interference process? And we, as humans, hate mysteries. So we're trying to answer that question to be able to understand who are they actually. So imagine this. Cosmic rays from deep space hit the atmosphere, and they give birth to neutrinos. These neutrinos start their journey, crossing the Earth while constantly changing their identity. And then we catch them in Antarctica. But why? Because we need a huge transparent detector. Ice in Antarctica is perfect. It's dark, stable, and extremely clear. And more importantly, it allows us to detect neutrinos coming from below, which means neutrinos that cross the Earth. Why do we care? Because neutrino oscillate depends on distance and energy. If a neutrino travels far enough, it should disappear, so the Earth become our laboratory. Good afternoon, ladies and gentlemen. My name is Gita Rahimi, and today I'll talk about how we can actually see neutrino oscillations directly in data using IceCube at the South Pole. At first, neutrinos in standard model are assumed to be massless. However, neutrino oscillation immediately implies that this assumption cannot be correct. Oscillation requires the existence of at least two different neutrino mass eigenstates with distinct masses. So, flavor states are therefore quantum superposition of mass state. This relation is described by the PMNS matrix, named after Pontecorvo Makinagawa and Sakata. The PMNS later plays a role analogous to secant matrix in the quark sector, but now describing neutrino flavor mixing. Conceptually, this means the neutrino flavor basis and the propagation basis are not identical. That mismatch is the origin of the oscillation. And by the way, the U alpha I here is the mixing matrix. Later, we will see that this is the PMNS matrix. Now, imagine a neutrino propagating through space. Each mass eigenstate evolves with a slightly different quantum phase because the masses are slightly different. Over time and distance, these phase differences accumulate. When the mass components are projected back into flavor states during detection, interference occurs. Depending on the relative phases, the interference can be constructive or destructive, leading to change in flavor detection probability. This is why oscillation is fundamentally a quantum mechanical interference phenomenon. One remarkable aspect of neutron oscillation is that microscopic quantum effects remain observable over enormous macroscopic distances, even across planetary scale. So this is the PMNS matrix that contains several mixing angles and a CP violating phase. We also see here we got Majorana phase, but this term actually could be absorbed in the neutrino state. So it's really depend on what model that we use. But we want to highlight the mixing angle here because the different angles basically emerge from different misters. Historically, it's actually coming from different experimental anomalies. That one true become associated mainly with solar neutrino oscillation, theta 2-3 with atmospheric neutrino oscillation, and theta 1-3 with reactor or accelerator neutrino experiment. This separation is not accidental. Different experiments probe different oscillation sectors because they operate at different baseline and energy scale. Since oscillation depends on the ratio between distance and energy, each experimental regime becomes naturally sensitive to different mixing parameters. First, we will talk about the solar neutrino problem. That was the major neutrino anomaly based on the history. Solar models predicted a certain electron neutral flux produced through the nuclear fission of the sun. But experiments consistently measure significant fewer electron neutrinos than expected. We see that from standard solar model, we will have a lot of neutrino electron that they actually produce a lot of neutrino electron that, and they also calculate the total flux, which is about 10 to the power of the 10. But in 1968, Homstake experiment only measured about one third of SSM prediction or standard solar model. And also later on, another experiment like Galax Sage Super Kamiokande for solar experiment also confirmed the missing flux for the neutrino electron. Later on, SNO experiment or Sudbury National Observatory in Canada, through neutral current detection, they found that about two-thirds of the electron neutrino have converted to mu neutrino and tau neutrino. So basically, we find that based on the different detection method, they found out that the missing flux of the neutrino coming from the sun is basically because of the oscillation that's happening. It's not because of the problem with the solar model. Because at the first thing, they thought that they were having a wrong model. And about solar neutrino, we usually see that they have low energy, real long baseline for approximately around 10 to the power of 8 kilometers, and they also that also Mikheyev Smirnov Wolfenstein effect for the electron neutrino. That's why mostly for the theta 1-2, we have it with the solar neutrino because only the electron neutrinos that actually need to going through the MSW effect because of the matter enhanced oscillation inside the dense solar interior. So, based on that reason and the condition, oscillation for this particular problem dominantly sensitive to theta 1-2 and the delta m square 2-1. And second one is the reactor experiment. A different story emerged from reactor neutrino experiments. Nuclear reactors produce intense fluxes of electron antineutrinos with relatively low energies and kilometer scale. So we have low energy and small scale. Baseline. For a long time, many physicists suspected that theta 1-3 might actually be zero because its oscillation effects appeared extremely small. However, experiments such as Diabe, Reno, and Double Choose found that it's not actually equal to zero, but it was like really, really small, but it's not zero. This result was extremely important because a non-zero theta 1-3 opened the possibility of measuring CPU violation in neutrino sector. In many ways, the discovery of theta 1-3 transformed neutrino oscillation physics from simply established oscillation into a precision era focused on detailed structure and symmetric properties. So even though the value of theta 1-3 is really small, it's still very important because later on they found out that CP violation could be actually measured by this. And based on this reason, the reactor experiment is really sensitive to theta 1,3. And this is what we focus on, which is the atmospheric neutrino. Unlike solar or reactor neutrinos, atmospheric neutrinos span broad energy range and enormous baseline variations. They are produced mainly through pion and kaon decay following cosmic ray interactions in the atmosphere. Some atmospheric neutrinos travel only short distances downward toward the detector, while others transverse the entire Earth before detection. That's why we have a broad range of high energy, because the cosmic rays will like release a lot of energy, and also long travel distances from around 10 kilometers to like approximately 13,000 kilometers, because like it's the diameter of the Earth. And based on that reason, this condition is really sensitive to delta M32 squared and the theta 23. And historically, back again, the ratio of the neutrino muon and neutrino electron based on the reaction that happened in the atmosphere is expected to be around 2, because we find here that pion will decay into muon and muon neutrino. So we have one muon neutrino here, and also later this muon will decay into another neutrino muon. So and one neutrino electron. So we should have more muon neutrino than electron neutrino. But the Kamiokande experiment in 1988 reported an indication of deficit of the muon neutrino flux. And also the upward going of muon neutrino is also gone. So they found that they found a asymmetric flux that should be symmetric. But later, about 10 years after that, Super Kamiokande observing a significant deficit of upward going neutrinos, and with zenith angle asymmetry exceeding around 6 sigma. And they found out that basically for the atmospheric neutrino, they also go in through the neutrino oscillations. So that was the first compelling evidence for atmospheric neutrino oscillation. For atmospheric neutrinos, the dominant transition is muon to tau, especially for IceCube. This expression shows that oscillation depends fundamentally on the ratio between propagation distance L and neutrino energy E. The parameter theta 23 controls the oscillation amplitude, while theta m squared 32 controls the oscillation frequency. And also later on we will find that the or the length of the propagation we will have from the zenith angle reconstruction. That's why it's really important to like reconstruct the data from the zenith angle, and also for the E, it's just like the energy reconstruction after CNN, of course. So there's two types of atmospheric neutrinos. The outgoing neutrinos travel only short distances through the atmosphere, typically around tens of kilometers before reaching the detector. In contrast, outgoing neutrinos must cross the Earth before arriving at IceCube. Their path lengths can reach almost 12,800 kilometers, or like maybe around 13,000, while the other travels through the entire Earth. I mean, like one could travel only around tens of kilometers and the other like thousands of kilometers. And according to the oscillation formula, those two neutrinos should behave very differently, because one, for the outward-going neutrino, it has much more time to evolve quantum mechanically. meaning oscillation become much stronger. This leads to a very concrete prediction. Some upward-going muon neutrinos should disappear. More precisely, they oscillate mostly into tau neutrinos, since tau neutrinos are difficult to identify efficiently in this energy range. The effect experimentally appears as a deficit of muon neutrinos. This is the most elegant aspect of atmospheric oscillation physics, that the Earth itself becomes the oscillation baseline. We'll talk about the IceCube, which is a detector that we are using to detect the atmospheric neutron oscillation. So basically, IceCube is a gigantic Cherenkov detector instrument station, roughly 1 cubic kilometer of Antarctic ice. So we'll literally use the ice for the medium of the Cherenkov radiation. And detector consists around 5,000 digital optical modules, which is, it's basically photon multiplier inside it. And also these modules are concentrated below approximately 2 kilometers below the ice. And why we have to go that deep? Because in that region, ice becomes extremely transparent and optically stable. And also, the detector later will not directly observe neutrinos. Instead, neutrinos occasionally interact with nuclei in the ice, producing charged secondary particles such as muons or particle showers. And these charged particles move faster than light propagates through ice, so they will emit Cherenkov radiation. This is analogous to a sonic boom, but with light instead of sound. The DOMs record the timing and the intensity of this Cherenkov light, allowing reconstruction of the original neutrino event. Because neutrino interactions are extremely rare, the detector must be enormous. Most neutrinos coming from below the Earth will never interact at all. So IceCube essentially solved the problem statistically by instrumenting an absurdly large volume. Yeah, that's why we made it really huge. This analysis specifically uses the deep core subarray inside IceCube. So basically, there's some region in IceCube. Specifically, we're using the deep core subarray because it's denser region on the detector, and they also instrumented with additional strings and optimized optical spacing. Because of that, we will have increased sensitivity to lower energy neutrinos in the approximate range from 5 to 100 GeV, which is precisely the region where atmospheric oscillation effect become the strongest. Once Cherenkov photons are detected, they are converted into digitized electronic pulses. From these pulses, IceCube extract timing information, charge distributions, and spatial heat pattern. These observables become the input for event reconstruction. However, reconstruction is extremely challenging because the detector environment contains substantial background, especially atmospheric muons produced directly by cosmic rays. So it's like over the South Pole. Like we don't want that. Distinguish genuine neutrino event from detector noise and atmospheric muon contamination becomes one of the central challenge of the analysis. So that's why we are using CNN. And this is the important improvement in this work because it has like around 5,000 times more robust interpretation of every single event type compared to the traditional analysis method. And also we have around seven times statistical multiplier. And also, after the reconstruction and like a lot of analysis going through, we will have around 150,000 pure neutrino candidates coming from 9.3 years of continuous observation. So this is a remarkable example of machine learning directly enhancing experimental sensitivity in particle physics. So it's really extremely useful. This is the um, reconstruction architecture, basically. So the CNN, we use 5 independent CNN convolutional neural network. Um, there are energy constructions, init angle interaction vertex reconstruction, particle identification, and also atmospheric muon classification, of course, to distinguish between the um, background and the one that we want to find. And also, the network architecture itself contains 2 parallel branches with 8 convolutional layers each that are combined into one dense output layer. The input feature comes directly from DRM signal, including like total charge, first hit time, last hit time, and basically other. And only hits the one that we wanted that is only hit within the certain range of time, like it's around nanosecond. Select the timing windows relative to the deep core trigger that will be used to in order to suppress detector noise. The training strategy is extremely important because machine learning analysis can easily introduce hidden biases if not handled carefully. So, the CNNs are trained using Monte Carlo simulations, but importantly, there's no physical weighting. Because of that, it actually prevents the network from artificially learning expected oscillation distribution. Instead, the goal is for the CNN to learn detector behavior rather than reproduce theoretical expectations. So we don't want the, the result to be like fully making fake data because if we add the physical weighting, there's a chance that they just like reproducing the fake data because they want to make it really similar to the what the real answer that we want, but we don't want it to be like that. So we use separate data set that used for different reconstruction tasks in order to minimize analysis bias. The training samples are designed with approximately flat energy distribution, also flat zenith distribution, and balanced classification levels. And we also use muon neutrino charge current track light events for the main reconstruction network. So at the end, the network is not being told where oscillation should appear. The oscillation signal emerged later from the construction experiment data. This is like the step of the reconstruction. So from the raw triggers, from the billion of atmospheric muons and random noise events, we actually use the containment energy cuts to like discriminate the energy or like arriving from near or below horizon and also the vertex. And also after that, we we going through the fatal cuts to reject events that hit the top 15 layers of or outermost strings to remove coincident muons. So we don't want to the data to be like in the edge of the range. And also we use the quality filters to basically we made a requirement to have more than 70 OM hits near deep core and at least 3 unscattered photon hits. And after that cut and filters, we finally used the CNN and BDT classifier And we use a score over 1.8 for the boosted decision tree. And after that, we finally have this final output, which is that much neutrino candidates. And we just leave and reduce the muon atmospheric background to around only 0.6%. At this stage, it becomes important to understand the topology of different neutrino interactions inside IceCube. The reconstruction quality really depends strongly on neutrino energy. At low energies here, fewer photons are produced and fewer DOMs become activated, which worsen angular and energy resolution. And at higher energies, larger light yields improved reconstruction performance considerably because atmospheric oscillation measurements rely heavily on estimating the neutrino propagation distance through the Earth. Directional reconstruction becomes critically important. This is why neutrino charge current events dominate the oscillation sensitivity of the analysis. So basically, the higher energy is will generate stronger Cherenkov signals, and therefore it will be easier for the detector to detect the data, and it's easier for the machine to reconstruct the data. So after that, this naturally leads to the particle identification parameter or PID. There's like several classes that we want to separate to identify like which particle it is that that produce or like going through the detector. Low PID values correspondly mainly to the cascade-like event. So here, and mostly this cascade coming from electrons or hadronic showers, it means that electron neutrinos here, and they also usually have intermediate or lower energies, and we will give them low PID scores. And if we got like the mix data, like the topology of the detector of the data, it's more like scattered. It means that it could be mixed. It might be electron neutrinos or other, but it also could be the muon neutrino. So we give it the PID score like in the middle of it. And this distinction is very important because the oscillation signature is expected to appear most clearly in the high PID region. This one, that later will dominated by muon neutrinos because muon neutrinos have like higher energy, so they will produce a straight track, and we call them track-like event. This figure is one of the central results of the entire paper. Here, the information is projected into physically important quality L over E. You can see this here. Oscillation physics fundamentally depends on this ratio, like what we already talked before, what we already discussed before. So compressing the data in this way allows the oscillation signature to appear much more clearly. The dashed histogram corresponds to the no oscillation prediction, while the black data points represent the observed IceCube events. In the cascade-dominated region on the left side here, the oscillation signature is less visible because directional reconstruction is weaker and even composition are more mixed. We can see like from different color means like it's different particle identification. We can see that it has all of the color, I guess. And we can also see for the between dashed and straight line for the total Monte Carlo simulation and the no oscillation simulation, it's like almost overlap. Yeah, it's just like a bit of deviation here. And we also see it for the mix. We still have like mixed particle unification here, even though we already see like the deviation between the no oscillation simulation and the oscillation one. But if we see on the high PID, PID track like region here, the deficit becomes extremely clear. Like it's really, I think it's pretty like the division is pretty high. The observed event rate falls significantly below the oscillation expectation, exactly in the oscillation sensitive region. This is like the black dot here, and we can see the straight line, like it's almost hit the same place, like it's overlap. And basically, this deficit is the direct manifestation of atmospheric neutrino oscillation in the data. Importantly, the structure does not emerge from one or two isolated events. It appears statistically across the entire construction sample. In a very real sense, this plot shows quantum interference becoming experimentally visible at planetary scale, and also we can distinct from this graph that almost particularly here that constructed is basically only for the muon material, which is blue, and others like it's smaller. So we can see here the oscillation signature appear really clearly. We can also see the event distribution. I mean the oscillation signature from the event distribution. So it's basically like the 3D kind of version of the same graph as before, because we also um, plot the reconstruction between the cos theta zenith and the energy. So it's basically between L and E. And also we want to see the distribution for the event. Let's see that on the right diagram here, we can see the same oscillation signature, but with different explanation. We see that here, the color, it's like a bit dark, which means the muon neutrino is disappeared in this region. And we all know that L over E, this is basically between the y-axis and x-axis. So we will have the diagonal line, and basically we see a bit here. So when immediately you notice a diagonal deficit region, this deficit is not random detector inefficiency. It corresponds precisely to neutrino with the appropriate combinations of energy and baseline to maximize oscillation probability. The zenith angle determines the path length through the Earth, while the reconstruction energy determines the oscillation phase through the L over E dependence. In other words, these diagonal structures is effectively the geometrical imprint of quantum interference. The detector is literally observing a fewer more neutrinos than expected in exactly the region where oscillation predicts disappearance should occur. Of course, real experiments always involve systematic uncertainties. In IceCube, these uncertainties come from separate sources. Detector-related uncertainties include like DOM efficiency, the ice absorption, and optical calibration, also the timing uncertainties. And also environmental uncertainties like coming from, like the entropic ice, and also the anisotropic scattering and birefringent polycrystalline ice. Yeah, it's basically the ice thing. And additional uncertainties come from atmospheric neutrino flux model and neutrino interaction cross-section. The analysis therefore includes nuisance parameter describing these effects directly inside the likelihood fit, which is this. The oscillation analysis itself is performed using a bin likelihood approach. The likelihood compares observed event counts with the predicted event distribution. So we compare them. That the predicted event distribution was generated under different oscillation hypotheses. And for the second term, we also include both oscillation parameters and systematic nuisance parameters simultaneously. So the second term is to like correcting the first term. It's like penalize unphysical deviations of nuisance parameter from their prior expectation. Interestingly, most systematic pools remain relatively small after the fit. So we see that it's like most of it, like it's still around zero, like just some of it appear to be like close to one, but it's still like there's no extreme tuning required. So we find that the likelihood analysis here and the simulation and the construction indicate stable fit and reliable oscillation result. In other words, the oscillation interpretation emerged naturally and robustly from the reconstruction event distribution, like we're not making up the data. And find a fit using the previous equation, values of delta m squared 32 and theta 23 consistent with the global Neutrino oscillation picture. The best fit for the differences between mass squares of 32 is around 2.4 times 10 to the power of minus 3. And for the mixing angle, which is the sinus square of theta 23 is around 1.54. And we can also look here for the IceCube. The neutrino oscillation is basically consistent across completely different experiments. It's actually show that like from another experiment we have similar result. Like it's the amazing thing about that. More of that, we want to like compare it where the data come from. We want to compare between the IceCube that coming from the atmospheric neutrinos and also using detector in Antarctic ice Cherenkov, and we use the natural source from the high statistic atmospheric oscillation. We compared with other experiments such as Super Kamiokande. They also use the atmospheric source, but the difference is they're using water Cherenkov. So it's different between water, like they're using pure water compared to the ice in Arctic. And we say that what's special about Super Kamiokande is basically they discover the oscillation of atmospheric neutrino. And also for the T2K, Tomioka to Kamioka, I guess, they're also using water Cherenkov, but the source of the neutrino is coming from the accelerator in Tomioka. And they actually used to research about the CP violation. We see here it's smaller because what interesting about accelerator source is that you can control the flux of the neutrino electron, whereas in IceCube it's coming from natural source, so we cannot really we cannot control how much we want about the neutrino electron. So that's why here they got smaller cylinders compared to the IceCube. And also for Nova is in Fermilab. They're using scintillator detector, so it's the detector itself it's different. And what interesting from Nova is they're mostly studied about the hierarchy problem. And also minus plus, they also using the same accelerator, but the detector model is more into the iron calorimeter, and they propose is actually to neoneutrino precision study. So if you like want to find out what it actually looks like compared to IceCube, it's actually the same one. Like it's always underground anyway. So it's basically like that. So we're finally coming to the conclusion. Hmm. So IceCube independently confirmed atmospheric neutrino oscillation, but compared to the other oscillation, neutrino oscillation that coming from another experiments, it's unique because they achieve it using natural atmospheric neutrinos traversing Earth. Like we're using the Earth as the mediator, as the detector, and also because of that, we got much higher energy over longer baselines that cannot be produced by another experiment. And also, from all of this result, IceCube also support the standard three-neutrino paradigm of neutrino mixing. And for the next upgrade, they want to improve the construction, higher precision, stronger sensitivity to oscillation physics, and hopefully they can found like a new physics coming soon. Okay, so it so it all coming it all started with a tiny particle, muon neutrino in the atmosphere. Like they were born in atmosphere. They later changing identity into something that really different from muon to tau, which is different flavor, different identity. And from fewer photons that we detect, we try to recreate the entire journey of this tiny particle. We're trying to understand why they're changing, like how they're changing into something that completely different. And at the end, we see that the more we understand neutrinos, the more we understand the universe itself. Thank you for watching. Bye bye. This is the references if you guys want to know anyway. Bye bye.